Welcome to Astronomy, Exploring Space and Time. This is our first live session, and I'm looking forward to answering your questions. It's been a great start to the course. You've been lighting up the discussion boards, viewing a lot of videos, doing the quiz questions, and there's 18,000 of you, so looking for some excitement in the Q&A. And all things are open. I'm an expert mostly in my research on cosmology, distant galaxies, and black holes, but I've sort of made it my business to learn about exoplanets and the solar system and more nearby stuff, so I'm happy to take questions. And in the manner of true scientists, I will not be shy about saying I don't know occasionally.
All right, so the first question is, some astronomers have speculated that we may actually be, some astronomers have speculated that we may actually be descendants of Martians. Apparently, they base this on the hypothesis that a meteorite that landed on Earth a long time ago could have polluted the Earth. Is there any logic behind this reasoning, or is it completely bananas?
Good question, and it's not completely bananas, but it turns out it may be a long shot. The logic behind the question is the fact that we know that rocks can travel through the solar system. There's a very inefficient interplanetary transport system based on impacts that launch small rocks into space where they can travel between planets and occasionally land on another planet. Now, this mode of transport works fairly well going from Mars to the Earth, because from Mars to the Earth, you're leaving a weaker gravity field and a very small, thin atmosphere, and going towards the sun in favor of gravity direction. So this is a more likely situation than the reverse process. It's far less likely for an Earth rock to go to Mars than for a Mars rock to come to the Earth. Also, there's a NASA website where you can look this up, and we know of, I think it's over 50, close to 60 Martian meteorites. That is, meteorites that have been examined and where the geology and the inclusions of trapped atmosphere perfectly match the Martian atmosphere, so it's beyond any doubt that these rocks came from Mars. Those 50 or 60 Martian meteorites are, of course, a small subset of the total number of Mars rocks that have landed on the Earth, most of which are unrecognizable. The Martian meteorites tend to be found on the Antarctic plateau, where they sort of stand out on the ice pack. As for whether life could have come from Mars, that's a harder question to answer, and of course, it's pure speculation. Another piece of the story is the fact that other types of research have demonstrated that microbes situated within a Mars rock, say something about the size of a small potato, that rock, when it lands on the Earth, going through the Earth's atmosphere, even at high speed, gets not much above room temperature deep inside. And so it is possible for a microbe to survive within a rock, the passage from Mars through deep space vacuum to land on the Earth intact. So it is conceivable that a living microbe could survive in a wait state. That trip might take tens of thousands of years, depending on the orbits of the Mars and Earth at the time. So those are the pieces of the story that make it not impossible, while slightly implausible, that a microbe could have got to the Earth from Mars. And so the speculation then goes that how could we tell that life on Earth, which formed, we think, close to 3.8 billion years ago, that's the oldest evidence we have, could have been from a Mars rock? It's actually an impossible hypothesis to disprove at this point. Of course, we hope to find life on Mars eventually. It won't happen in the near term. And if we find life on Mars that has a completely different biological basis than the Earth life, then that will be an independent origination. But if we find life on Earth that has the same biological basis as the Earth, that will bring this hypothesis back into view. Maybe both lives originated in the same way and it started on Mars, and we are indeed Martians.
Okay, so that question, just to clarify, was from Gail. So thank you, Gael, for submitting that. The next question that we have, is about the size of the universe, and this is from Aisha. While reading your online textbook, you mentioned something that I'm unclear about. You stated that our universe is 46 billion light years in any direction away from Earth. If the universe is 13.7 billion years old, how do we arrive at 46 billion?
Yeah, very good question, and you're anticipating material that we'll come to in the second last week of the course, but let me explain it now. Yes, logically, if the universe is 13.8 billion years old, you might imagine that it would only have an extent of 13.8 billion light years in any direction. The reason why the distance to the edge of the observable universe is roughly 3 times larger is because early in its history, early in the history of the Big Bang, all points in space were separating by faster than the speed of light. Essentially, we would say the universe was expanding superluminally. This was essentially true for the first 5 billion years of the expansion. Immediate reaction, well, doesn't that violate special relativity? Nothing can travel faster than light. Special relativity applies to light signals sent through a local situation like a laboratory or the solar system or even our own galaxy. The situation of the universe itself is governed by general relativity, not special relativity. It's the superior theory of gravity. And interestingly, general relativity has no speed limit built into it. In other words, in general relativity, if space-time is expanding, there's no speed limit to this expansion. It can expand as fast as it wants, given the right amount of energy. And indeed, in the history of our universe, it appears that the universe was initially expanding faster than light. And so that means that we can see points in space that have been carried far further than you would imagine light could have traveled in the age of the universe because of that superluminal expansion. It also implies that there are regions of space that we haven't yet seen, that we will one day see if we wait long enough for light to reach us from those distant regions.
All right, the next question is, I know that the moon is moving away from Earth at a rate of about 0.04 meters a year, but will there come a point in the distant future when the moon will actually start to approach the Earth again?
So that's an interesting point, this very, very subtle change in the gravitational situation where the moon is indeed moving away from the Earth. And this is just basically energy conservation. As we know, the moon is tidally locked to the Earth. So there's clearly not just a gravitational interaction that keeps the Earth orbiting, the moon orbiting the Earth, but also a tidal force that keeps the moon facing one side to the Earth. And so in conservation of energy terms, the lowering of the energy of the orbit of the moon by gradually slowing down also corresponds to it slowly increasing its distance from the Earth over time. It's a very subtle effect. That tiny amount per year, less than an inch, it seems imperceptible, but actually because we left reflectors and experiments on the moon during the Apollo era, we can bounce signals off the moon and very accurately measure the distance to a millimeter or so. And so this increasing distance to the moon has been measured. It's actually been measured with instruments left from the late 1960s. So we believe this will continue, and it's very hard to play it out into the very distant future, because if you project the gravity equations, you're having to follow the Earth-Moon orbit. If you follow it, say, millions of years, you're following it for tens of millions of orbits. And gravity, even in a two-body situation, there's influence of other objects. So it's not an absolute, it's not a perfectly precise calculation. And so I would have to say that the long-term projection of what this means over billions of years is uncertain. It depends on the orbital calculations that are never completely precise. But indeed, the moon will continue to move away, and at some point it may stop being tidally locked to the Earth.
All right, so this question is from Karina. Could astronomy play the main role in climate change? Are cosmic rays or solar variation or whatever more important than carbon dioxide?
It's a good question, and it's the subject of very active research. And some controversy, of course, because there's the issue of climate change and what causes it is not completely resolved by science. The fact of temperature increase beyond what we can naturally explain by other phenomena seems to be beyond doubt, but the mechanisms are not clear. The primary cycle at play in astronomy is, of course, the solar cycle, the 22-year cycle where the sun's magnetic field reverses, the sunspots go to a minimum, back to a maximum, and then down to a minimum again. And that corresponds to changes in the sun's radiation on the Earth. The sun also couples to the Earth by cosmic rays and through its magnetic field, which extends out into space, and what's called the solar wind, these high-energy particles that hit the Earth and are essentially deflected by our magnetic field. So the sun is definitely coupled in fairly profound and subtle ways to the Earth beyond the simple radiation that falls on us. The variation of the radiation due to the solar cycle is very modest. the total brightness change in the sun from one part of the solar cycle to another is less than 0.1%, 1 part in 1,000. And that alone is, of course, not sufficient at all to explain any variations in the Earth's climate. But if you go to longer, well, actually shorter or longer wavelengths, but most importantly, the shorter wavelengths, ultraviolet and X-rays, the sun's variation in the solar cycle is more extreme. It can be tens of percent. And that, of course, due to the interaction of those high-energy waves with the Earth and the cascading effects through the atmosphere of the Earth and the magnetosphere, can have more significant climactic effects. We also know that the more long-term variations in the sun's cycle, its sunspot cycle, has affected the climate of the Earth. There was a time called the Maunder minimum, which was a historic low over a number of cycles in the sunspot counts that occurred within 100 years of the invention of the telescope in the mid-17th century. That time in Europe corresponded to what's called the Little Ice Age, when temperatures were so cold that lakes froze over even in southern Italy. And in places like Holland, things were frozen essentially all year round for a period of time. So there's evidence within the last 400 years that more dramatic variations in the sun's activity can be coupled to climate. However, these do not of themselves explain the monotonic increase in the Earth's temperature over the last 150 years. While we don't know all the mechanisms that are in play, the tracking of the Earth's increase in surface temperature and water temperature, where it's measured, with the increase in carbon dioxide and the strict correlation with that with industrial activity since 1750 is one of the best correlations in science. So at the moment, the null hypothesis that climate change or global warming is caused by atmospheric gases caused by industrial activity, carbon dioxide primarily, is the best supposition. But I would say that the research is still open, and so there are people who recognize that we don't fully understand the interactions between the Earth and the Sun astronomically, and those are still under active investigation.
All right, the next question is from Mohammed. What exactly is the James Webb Telescope?
The James Webb Space Telescope, the first question people ask is, what is the James Webb Space Telescope and who is James Webb? Even astronomers, to be honest, were slightly disappointed in the naming of this telescope. The Hubble Space Telescope, which it replaces, was of course named after one of the most prominent astrophysicists, perhaps the most famous astronomer of the 20th century, Edwin Hubble. Its successor is named after a mid-level and eventually a senior NASA administrator, sort of forgotten now because he was an administrator about 40 or 50 years ago. So that was not NASA honoring one of its own. And I'm sure if NASA had asked astronomers, they would have picked one of their own to name this telescope after. The James Webb Space Telescope is a very ambitious project. Hubble is well into its third decade and still doing excellent science after 5 servicing missions. But Hubble is a small telescope, 2.4 meters. If you put it in a list of the world's largest telescopes, at this point, I don't think it would crack the top 30 or even 40. So it's not one of the bigger telescopes. It's very expensive to put telescopes in orbit. Hubble's size was essentially reverse engineered to be the biggest thing you could fit in the shuttle bay, with the space shuttle as the launch vehicle for Hubble. And astronomers have long known that they needed a successor to Hubble, and they wanted it to be bigger, have more collecting area, since it's not a very big telescope. James Webb satisfies this. It's a 6.5 meter telescope and very ambitious in its design. It's not going to be in Earth orbit like Hubble. It's going to be at one of the Lagrange points, 1.5 million kilometers from the Earth. It's a very stable, quiet place to do astronomy, an excellent place to do astronomy. But once it's deployed, it's unserviceable. Astronauts will not go there. No shuttle or its successor will be able to go there. This is a telescope, once deployed, it has to work because there's no way to fix it. So the stakes are very high for this mission. It's also a telescope that has to unfold from a more compact package that's launched from the Earth and then taken out to the Lagrange point. It has to unfold and it has many moving parts, not just the telescope mirrors themselves, but the struts that hold the secondary, the sun shields, solar arrays. All of these things unfold or unfurl at a very remote location. And it's easy to think of all the things that could go wrong with this. It's a very ambitious and technically challenging project. It seems to have passed all its milestones. Along the way, its budget has ballooned to an uncomfortable level for most astronomers who would like to do other things and don't like one project taking all the money. James Webb's budget is somewhere over $8 billion, probably heading for $9 billion at the time it launches in late 2016. But when it does launch, it'll be the premier facility in space. That collecting area is an order of magnitude more than the Hubble Space Telescope. James Webb is designed to look for first light in the universe, the very first generation of stars and galaxies near the dawn of time, probably 300 million years after the Big Bang. It's also going to do excellent work looking deep into star-forming regions because it has excellent infrared instruments. It's also going to do some work on exoplanets, transits of exoplanets, and perhaps measuring the spectral signatures of atmospheric gases in exoplanets, a very exciting project. So everyone's looking forward to James Webb Space Telescope, but I'd say most of the engineers and some of the scientists are fairly nervous because of the technical challenges of this mission.
Right, the next question is from Vincent, and Vincent asks, hello, I must admit I'm not an enthusiast of dark energy. In the 17th century, scientists came up with the phlogiston theory. In the 18th century, it was discovered that phlogiston wasn't necessary to explain the facts. In the 19th century, scientists came up with the ether. Later on, it was discovered that ether wasn't necessary to explain the facts. Do you think that dark energy might be the ether of the 20th century, and then in the 21st century, someone will discover that it's not necessary to explain the facts?
It's an excellent question, and the question made with a great awareness of the lessons of history. I actually think even dark matter might fall under the rubric that you've described with your historical analogies. But let's stick to dark energy for a minute. First of all, what is dark energy? Dark energy is hypothesized to be the dominant component of the universe. If you make a pie chart of what the universe contains, 3/4 of the universe is this entity called dark energy, which is causing an accelerated expansion of the universe. Currently, less than 1/4 is dark matter, and all the stars and galaxies that we can see with our deep surveys and telescopes amount to only a few percent. So it's the dominant component of the universe, and it's causing the universe to expand faster and faster. So what is dark energy? Is it a real thing? And the simple answer is no. We don't know if it's a real thing or just a convenient phrasing or title for ignorance. All we know is that observations of supernovae in the mid-1990s showed, using them as markers of space-time, that the universe was currently accelerating in its expansion. Now that's not what you expect from a standard Big Bang. Gravity of all the galaxies and matter in the universe should cause the expansion rate to slow over time, not increase. In other words, this is something that operates opposite to gravity. It's like a universal repulsive force. Physicists search for some plausible explanation for something that worked in the opposite direction to gravity in terms of how it functioned. And they didn't come up with anything. There is something called vacuum energy that exists in physics. It's part of the quantum theory. But when you do simple calculations of vacuum energy and project them to the large regions of the universe, you get the wrong answer to explain the accelerating expansion. In other words, physics had nothing in its toolkit that could possibly explain why the universe was accelerating in its expansion. So given that physics has come up dry, some people are indeed dubious or skeptical that dark energy is a real thing. Or if it is a real phenomenon, the accelerating expansion, what is causing it is a more interesting question. And at the moment, it's the biggest unknown in cosmology, plain and simple. So I won't pretend to answer it because the answer is no one knows. It's a theoretically interesting landscape because given that physics has come up dry, theoretical physicists are working hard to imagine how space-time can accelerate in expansion. How can you generate energy from a vacuum? And I would say something like 150 to 200 research papers are written a year in pure theory to try and come up with dark energy. The problem in this field is that the observational side is not moving as fast as the theoretical side. And we might recognize that in the scientific method or in how science works, that's a sort of unhealthy situation when observations and theory are not working lockstep and closely related. It is extremely difficult to get an observational handle on dark energy beyond the measurement of the accelerating expansion itself. There are a few upcoming missions which are going to try and define dark energy in a slightly more subtle level, and in particular see whether the strength of the dark energy changes with direction in the sky or has changed with cosmic time. But if we don't get a handle on that, then we're really going to be struggling to understand dark energy. It is the biggest problem in cosmology.
All right, someone else has a question that's sort of related to quantum mechanics. What role does quantum entanglement play in the origins and future of the universe?
That's an interesting question. So we're into speculation here. Quantum entanglement is, of course, a real phenomenon, as bizarre and as counterintuitive as quantum theory is. Entanglement has been observed in very elegant experiments now. Entanglement has been observed over transcontinental scales. This has taken amazing experiments in lab physics, have taken us from showing quantum entanglement on a lab scale, 10 meters, to quantum entanglement between different continents. So quantum entanglement exists, which is to say quantum states are strangely linked at remote locations so that knowledge seems to be transferred instantly or simultaneously between remote states, and where if you interrogate one state, it determines the other state. Well, if quantum entanglement can exist over these large macroscopic scales of roughly the size of the Earth, who's to say that it couldn't apply on scales of the universe? But that is a large degree of extrapolation. So at the moment, the conservative approach is to say that quantum entanglement doesn't really affect cosmology or the universe as a whole. The simple answer, however, is that we don't know. These are almost impossible tests to make. I might note that John Wheeler, a very famous theoretical physicist in the second half of the 20th century, the person who coined the phrase black hole and wrote one of the pivotal texts on gravity in the 1970s, he speculated heavily towards the end of his life or his career about quantum entanglements or quantum effects that macroscopically are generated, possibly affecting cosmic scales. It was considered radical for him, even as a famous theoretical physicist, to talk about these things. The simple answer is that we don't really have an empirical way of measuring entanglement on the scale of a galaxy. And so we're kind of stuck testing that hypothesis.
The next question is from Scott. I recently read about the WOW radio signal that occurred in 1977. Can you please break down what occurred and why it was ultimately disregarded in your own personal opinion? Thanks.
Sure. The WOW signal is one of, in SETI, the Search for Extraterrestrial Intelligence, astrobiology and SETI are the subject of the last week of this course. SETI is designed to detect signals from hypothetical or putative intelligent technological civilizations remote from the Earth. And they've met with 60 years of what they call now the Great Silence, because nobody's really seen a real signal or one that's plausibly coming from an intelligent civilization. One of the early excitements in this field is something that was called the WOW signal. So this was based on a radio telescope, a football-sized field radio telescope that was hosted by the Ohio State University. It's since been dismantled, it no longer exists. And I think it was 1977. This telescope was observing, and they were using early technology. This is almost pre-digital technology. They were using a strip chart where the radio signal from the array was just being converted into a wavering pen that traced an inky line on a rolling ball of paper. And a large signal, a transient signal, was observed far beyond the capability of any local radio source. In other words, they were able to rule out, based on the timing of the signal, that it couldn't have been caused by a radio station or any possible transmitter near that radio telescope. Nor was there any known radio star like a pulsar in that direction of the sky. So this became a very puzzling signal, and the tech or astronomer on duty wrote "wow!" exclamation, or maybe triple exclamation afterwards. I have the image on my computer. I can't remember exactly what it looks like, but it's a pretty impressive burst of radio emission. The problem was it never repeated. Anytime in science or in astronomy you get an unrepeated signal, however exciting, you're left dubious as to being able to interpret it or whether it's real. Pulsars, of course, were repeated radio signals, and even they were originally and somewhat lightheartedly attributed to little green men. Jocelyn Bell, one of the co-discoverers of pulsars in 1967, she referred to her first three pulsars as LGM 1, 2, and 3. So the WOW signal was an extraordinary radio event that was never repeated, that I guess could have been caused by a pulse from a distant civilization aimed at the Earth. But if you don't ever get a repetition of that signal, and people have looked in that direction in the sky since, of course, then you're kind of stuck. So it just sits there as an anomaly in history.
All right, our next question is from Anonymous, but there are quite a few posters who are also interested in this. I don't think the universe cares what time it is, so my question is, does time exist, or is it merely a contrivance of man? It would seem that the universe can exist quite easily without time. Man needs time as a means to measure observations. The universe does not care how long it's been in existence.
Yes, that's a good question. It's almost tending into philosophy, and that's fine. Physics was, of course, called natural philosophy for hundreds of years at universities until the last century, in fact. And so some of the issues of cosmology are philosophical. So what is the ontological status, to use a philosophical term, of time in cosmology or nature? It's a good question. Does the universe need time? Time appears in general relativity, which is our best theory of gravity, but it's a fungible concept. Time, it depends on local gravity. It depends on mass energy. And so there's no absolute sense of time out of general relativity. And we know the extreme version of this. We know that clocks run slower in strong gravity fields. And of course, that phenomenon was tested with atomic clocks back in the 1960s, showing that an atomic clock on the Earth's surface ran very slightly slower, like about 1 part in 10 to the 14, from an atomic clock flying in a U-2 aircraft at high altitude. The extreme version of this, of course, is the supposition that at the event horizon of a black hole, time completely freezes. So that's a pretty good sense that time is a fungible, supple concept with no absolute meaning. If we can posit situations in our gravity theory where time freezes completely, and therefore, of course, time does not exist. So we could imagine, for instance, that a black hole at its event horizon and inside its event horizon is a timeless entity. We also know that there are situations where time has no meaning in the early universe. So in the very early universe, what would it even mean to run a clock? If we talk about time after the Big Bang in tiny fractions of a second, which I do in the last week of the course, it's based purely on a projection backwards from a more familiar terrestrial situation of a large, low-density universe. So time in the very early universe also loses its meaning. Space and time are tightly coupled, which is part of general relativity, and we don't actually have a theory to fully understand the extraordinary conditions of the Big Bang. So there's another situation where time has no meaning. And in that sense, time is an emergent property. There's also the supposition that time is an emergent property caused by the entropy of a situation. For instance, that if our universe had much higher entropy than it did, the time would have no meaning because events would flow equally likely backward and forward in direction, as microscopic subatomic particles do. The microscopic world does not have a very clear time arrow. You can posit nuclear reactions, and they will run equally well backward and forward in time. So the microscopic world, the quantum world, is also almost timeless. I think with all of these examples of timelessness or places where time loses its conventional meaning, we have to be very careful about being too absolute about our sense of time. And then, of course, human time, our sense of time, has a psychological component. The arrow of time, the sort of inevitable distinction between the forward-flowing uncertainty and the unreeling of events that we can record and have experienced. So no simple answer to that question. It's a great question. We could have a whole discussion on that alone.
The next question is from our old friend Julian. And Julian asks, how is the GMT coming along?
Hey, glad you're back, Julian. GMT is the Giant Magellan Telescope. That's our baby here at the University of Arizona, and of course it features in the Magellan telescopes in this course. The GMT is one of a handful of telescopes of what I'll call the next generation of large telescopes. The current largest telescopes in the world are roughly 10 meters, 10, 11 meters. We have one of those in Arizona. The twin Keck telescopes in Hawaii are 10 meters each. There's a Grand Canary Island telescope. It's about 11 meters. And that's sort of where we've topped out. The Giant Magellan Telescope is going to have an effective area, if it were one mirror, of about 22 meters. It's actually made of 7 8.4 meter mirrors put together like flower petals around a central element. At the moment, we've cast 3 of those mirrors. 2 have been polished. The 3rd is being polished. The 4th will be cast soon. and we're on track to start assembling that telescope. Because it's modular, because it has 7 mirrors, we can make a minimal telescope with a central segment and 3 of the petals symmetrically arranged. And that first light telescope, which will not have the full capabilities of the total GMT, but will have more than half the light gathering power and all the angular resolution, that's projected to take its first light, not quite clear, but maybe 2018, 2019. The site has been leveled in Chile. It's very near our regular Magellan telescopes, which are 6.5 meter twin telescopes. So we have the site, we have the infrastructure for the telescope, the partners are on board, and I would say of this $1 billion project, about $400 million has been hard committed by our partners, and another $200 million is sort of the checks in the mail. So we're on our way to funding this telescope, and it's very exciting.
The next question is from Sam. Professor Impey, I would like to know your views on the number of dwarf planets in our outer solar system. According to Professor Mike Brown, co-discoverer of several dwarf planets, there could be up to or over 300. What do you think of this?
Yes, Mike Brown is of course the deacon of this field. He works at Caltech. He wrote a really nice book, which I recommend, which has a great title as well. I'm jealous of the title. How I Killed Pluto and Why It Had It Coming. So if you're nostalgic about Pluto being a planet, you probably don't want to read that book. So Mike Brown has been personally responsible for finding one of the planets that exceeds Pluto in size and was part of bumping Pluto from the pantheon of planets and turning it into a dwarf planet. And he's also found more than a handful of other dwarf planet candidates where the size measurement and the mass measurement is just uncertain enough that they could also be as big as Pluto. These uncertainties are typically 30 or 40% because they're so far away. His supposition, it alluded to in the question, that there could be dozens or hundreds of more dwarf planets is based on the fact that we're talking about large distances. So as you go beyond the orbits of Neptune and Uranus, you reach something called the Kuiper Belt, and this extends from about 40 astronomical units, or Earth sun distances, to about 80 astronomical units. And then there's a sort of looser aggregation that tails off out to 100 or 120 astronomical units. Well, that's very far away. For things that are smaller than Pluto or similar in size, that are 100 times the Earth-Sun distance, these are obviously extremely faint objects. So getting an inventory of them is hard. The other problem is that these dwarf planets do not exist in a neat plane the way the planets of the solar system do. So as you know, in the solar system, the regularized orbits mean everything is found in the ecliptic, which is the path taken by the sun in the sky. So if you want to look for a new regular planet, you look in the ecliptic, and that's a pretty narrow strip of sky. It's a zodiac. For these dwarf planets, they're in a kind of puffed up disk-like distribution. And the puffiness of the disk, that sort of vertical dimension of it, means it spreads out over 10 or maybe 15 degrees on either side of the ecliptic. And that means it's a very large swath of sky to survey. So to find all of these objects, you're having to do 3 things. You're having to survey a very large chunk of sky, you're having to look for very faint objects, and you're going to have to track them for years, because out of that distance, by Kepler's law, they're going to be moving very slowly. And that's almost imperceptible motion on pictures or CCD images taken months apart. All of this means it's a tall order to have a complete inventory. So I think Michael Brown is using the handful of objects we do know, which tend to be in the relatively nearby regions of the Kuiper Belt, and he's trying to just roughly extrapolate how many there might be in the more full volume available to observations. It's going to take about a decade for us to fully survey that volume. Those surveys are underway, so it will happen. And it is indeed likely that out of those surveys, as many as half a dozen, maybe a dozen objects larger than Pluto will be found, along with dozens and dozens, maybe hundreds that are similar in size to Pluto.
Next question is from Tracy. It seems that mathematics and the principles of logic are the 2 languages used to describe physical and scientific phenomena. Does anyone think there will ever be language other than these that will emerge that will better describe scientific, physical, or material science? If so, where might the language come from?
So it's an interesting question of how science works at the level of the toolkit, the fundamental toolkit. The universe is very well described by physical laws that have mathematical expression. they have their expression in mathematics that, to the view of people like Einstein or Chandrasekhar, one of the great astrophysicists of the 20th century, is beautiful and elegant. General relativity is maybe brutally hard if you have to study it in grad school, but it's extremely efficient, compact set of differential equations, second-order partial differential equations, packed down into a form that really is one line. And yet it describes everything in the universe and the subtleties of curved space-time. That, to a physicist, is extraordinary. It speaks to the power of mathematics to describe nature. The use of words to describe science or to describe nature is more interesting. The landmark case here came from Bertrand Russell and Alfred North Whitehead, very famous philosophers in England in the early 20th century. One of Russell's life works was to put into words, to use words and logic converted into words, the symbolic logic or the mathematical forms of logic that underpin physics. And he was able to do so. It's a monumental achievement that took him several decades. So we can map symbolic logic and mathematical logic into words, into sort of semantics, if you like, or verbal logic. And that's an interesting thing because it elevates the status of language in science to a very high level. It's not just that scientists talk to each other and use jargon and terminology that has a universal meaning, or that they use mathematics that has a universal meaning, but they also use words and construct arguments and logic in ways that should be recognizable to someone in another culture speaking a different language. What about a universal language? That's interesting too. There's a man who's not well known to the world of science or to the average person called Hans Freudenthal. He was a philosopher and a mathematician who worked in the 1960s and 1970s, and he went further down the road than Whitehead and Russell, and he posited a universal language based on logic, and he called it LINCOS. I can't remember, it's an acronym, and I can't remember what the acronym stands for now. But he actually developed a complete and self-consistent language based on logic, just following the same agenda. And he went further to say that if we were to communicate with extraterrestrial intelligences, rather than sending streams of numbers at them, or prime numbers, or little pictograms, or whatever it is that we've done so far, we should use this symbolic language to send messages, because he assumed, or he made a supposition, that it might be universally comprehensible. Nobody knows if that's a correct supposition, but it's an interesting idea.
Right. The next question is somebody who's watching live who asks, can there be any substitutes for water and carbon as prerequisite requirements for life, such as, say, methane and silicon?
Yeah, really good question. The issue with astrobiology is an important one, that we sort of look for life as we know it, because that's what we know how to do, and that's also what will return a clean answer. As you probably know, NASA's mantra in astrobiology is follow the water. So NASA, in designing missions for Mars or wherever else NASA is sending missions in the solar system, is essentially accepting water as a prerequisite for biology of any kind. That's an assumption, and it provides a good way forward, but is it an absolute and a necessary assumption? The jury is out on that. We essentially don't know. It appears that life needs a liquid medium. Life needs a medium for complexity to grow by chemicals bumping into each other and growing in complexity over time, and water provides that. However, to a chemist or a biologist, water is a very mixed blessing. Water is also slightly corrosive. There are situations where water can dissolve or dismantle molecules just as well as it facilitates growing larger molecules. And to some biochemists, it's not obvious that water is the best medium for building complexity in life. What are the alternatives? Well, we don't know. There are chemicals like glycol that are possible liquid mediums for forming complexity. There's the methane-ethane mixture that we've already found on Titan. And we simply do not know whether it's possible to build complexity in a biochemical network in a mixture of ethane and methane. And on Titan, it's actually got small amounts of ammonia and water mixed in. So these are entirely plausible suppositions if you want to define strange alien forms of life. And especially because of Titan, as an example we hope to one day visit again, I think people are investigating this both theoretically and in the lab as well as they can. So does life need water? Probably. every life form on Earth has water as part of its landscape, down to the level of 20% for the driest thing we know of, and 99% for something like a jellyfish, which is essentially all water in the ocean. But does it absolutely have to have water? Not necessarily. Probably a liquid medium of some kind, and there's a handful of other possibilities. They're not, however, as abundant as water. The other reason life might use water is it is available. Hydrogen, the most abundant element in the universe, and oxygen, one of the top 5 most abundant elements in the universe. And water vapor forms naturally in interstellar space. We know water is abundant throughout the universe. So maybe we don't need to look further because water exists. For carbon, it's not clear either, but I think the sense amongst biochemists is that carbon is so superior to any other basis for building complexity and macromolecules that it will be carbon that we find other forms of life centered on. People have investigated silicon. Silicon clearly sits in the same position in a different row in the periodic table, so it has many of the same electronic and chemical properties. But people who've investigated silicon either in the lab or theoretically can see very easily, and Steve Benner, someone who's done a lot of this work at the University of Florida, that the compounds formed with silicon are not as stable or diverse as the ones formed by carbon. Carbon's ability to make long, essentially infinite chains, essentially infinite diversity of molecules, is unsurpassed in the chemical landscape of the universe. So while life doesn't need to be based on carbon, again, carbon is one of the most abundant atoms. It's up there in the top 5 in cosmic abundance. It seems likely that life, if it exists elsewhere, will use carbon.
Next question is from Morton. Can we call Tycho Brahe a real scientist? With his observations, he laid the foundation for Kepler's law, but Tycho himself was not able to deduce the laws of motion from his own observations.
That's right, and as you probably know, asking the question the way you have, he didn't even believe the Copernican model. Tycho had his own strange hybrid of a geocentric and a Copernican model that essentially was completely wrong and wrong-headed. So Tycho did not believe the Copernican model, even though his observations, ironically, were used to support it by Kepler. As for him as a scientist, I think he is unrivaled in one way. Not all scientists are all-rounders. Some scientists are great with the math and lousy with the telescope, and vice versa. Tycho was one of those people who's a great observer, and I think astronomers would probably align in saying that he was the greatest pre-telescopic observer in history. He made naked-eye observations on this little island, once he got an island given to him by the King of Denmark. Then off the coast of what is now Sweden, then owned by Denmark, for about 24 years, I think, from his own observatory, Uraniborg. I've been there at a conference. It's a pretty amazing place. And he was relentless. He was indefatigable. I mean, it's a lousy place to do observing. It's in a pretty cloudy, cold, wet, nasty part of the world. I'm sure he didn't get many clear nights. But by working relentlessly for over 2 decades, he gathered, and then no telescope, just using octants and setting circles and just various modes of aligning of what is essentially a large protractor in the sky and measuring an angle. He made measurements of the planetary motions, in particular Mars, that were accurate. They were a factor of 5 more accurate than anyone else had done up to that point, or without a telescope. I think that alone elevates him to a very high tier of observers. But he was not very theoretically savvy. And in fact, that was the basis of him eventually taking on the brilliant young mathematician, esteemed as one of the best mathematicians in Europe, as his assistant later in his life. He knew he couldn't do it all. He knew he couldn't interpret his own data. And that was why he went into an alliance with Kepler.
Right, Adele asks, is there any scientific basis in the old wise tale that the phases of the moon affect our moods?
So people have researched this, and I don't know all the research, but I've investigated some of it. And it's not, it's an interesting question to ask, of course. And the most extreme version of this is lunacy, the whole idea of lunacy. So that's a more extreme version of a mood change. That's actually craziness caused by the moon. So there's a long history of this. The history of the idea of this goes back centuries, especially well documented in Europe. And because it comes up occasionally when I teach, I sort of went into the literature a bit. And there are a few individual studies that appear to show correlations of lunar cycle with mood, or with human behavior, or with the incidence of crime, or with psychosis, or with hospital admittances into the ER. I mean, all manner of them. I could make a list of 20 different correlations people have looked for. Of course, menstruation cycles are aligned with the lunar cycle. So there are, some genuine physiological bases for alignment with the moon itself. But as far as that sort of primordial lunacy hypothesis that extreme behavior is coupled with the moon cycle, while some individual surveys found statistically significant results, there was a very powerful, not just one, but actually 3 different what are called meta-analyses. That is, people who look at the data of individual studies and combine dozens or even hundreds of them to try and tease out a more powerful statistical result. Those meta-analyses within the last 10 years have shown nothing. Basically, when you take the increased statistical power of a whole set of surveys rather than individual ones where the sample size may be too small, you're left with nothing. So I would say, based on the best and most recent analysis, there's nothing there to explain.
All right, Vincent asks about defense systems that protect us from near-Earth objects. How long might it take to get one of those defense systems ready to work?
Well, we're a good part of the way there. We in Arizona have one of the telescopes that's part of the network, Skywatch, and there's now a couple of different networks. NASA was mandated by the US Congress 15 years ago, I think, to essentially identify all objects in the solar system that could potentially cross the Earth's orbit larger than 250 meters. And NASA's already got most of the way there. Not all of them, it's probably got 80 or 90% of them. So that's the goal. The goal of these telescope networks is to identify anything that's larger than a small asteroid that might possibly cross the Earth's orbit at some point in the future. That's the first stage. You don't need to defend against something until you know it's going to hit us. The next stage is to evaluate the risk. So the identification of these objects is going pretty well, and I would say probably within 5 years these Skywatch type networks will be operating at a completeness level where they won't be missing anything. The evaluation of risk, of course, depends on computation, orbital calculation. And so basically the strategy is, since you can't observe everything equally well, the strategy is when you see something based on orbital elements involving just a handful of observations, it looks like it might cross the Earth's orbit, you then start observing it more intensively. So you quickly home in on a list of possible Earth crossers. And then you keep drilling down. And as you drill down and get more data, in almost every case, since space is so big and the Earth is so small, these objects are predicted not to come really anywhere near the Earth, millions of miles away or more. For the handful that survive, or for the ones that survive, you bring increased computational power to bear, and you calculate their orbits even more accurately. And so this winnowing process continues, where you don't spend your time and attention or your computational power or your telescope resource on anything except a tiny handful of objects, a tiny fraction that could possibly hit the Earth. And it's known how to do that. These things the risk is classified, and you could search, I don't remember the NASA website, there's a NASA website, and nobody keeps a secret, that actually pulls out the objects that have the highest probability of hitting the Earth. And they're calibrated on something called the Torino scale, because I think the impact probability was worked out at a conference in Torino, Italy, a decade ago. And they're color-coded neatly on this website. Where if they're very unlikely to hit the Earth, like one in a million, they're green, and then yellow, orange, and red. And they only get up to red when it's like 1 in 100 probability. And if you look at this list at any given time, you'll see almost all green and a few yellows and maybe one orange, and not even usually an orange. So that makes people sleep better at night. The protection part comes in the last stage. If you do persistently, with better and better data, better orbital calculation, find something that still could be hitting the Earth, down at the probability level where you don't want to risk civilization on the chance that you're wrong, then of course you have to prepare your response. The advantage of these telescope networks is they're looking pretty deep. So they're finding objects, even though they're moving fast, where your lead time, your warning time, before they would get to the Earth intersection is certainly months and sometimes even a couple of years. So you do not have one of these doomsday scenarios that Hollywood likes so much, where they find the potentially impacting object and the clock is ticking down in the top right corner and you have hours to do it or days and it's all a big panic and you barely get there. We're going to have a lot of time. And actually the technology exists to send a space probe out alongside the object, turn around and track it, and use what's called a gravity tractor technique, which is actually using the mass of the spacecraft itself, just paralleling the impactor, the potential impactor, to gradually tug it away into a different trajectory. At that point, you do have to trust the rocket scientists that they got that right and didn't just tug it into an impact trajectory when it was going to just miss us. So, trusting the rocket scientists, I think actually all the pieces are in place to protect us, but the surveys are not yet complete. That'll take another 5 or 7 years.
Right, the next question is from Kevin, and he asks, do you know of an updated conservative launch date for the James Webb Space Telescope?
They're still talking late 2016, but a lot of the inside skinny at NASA is that it'll have to slip probably 6 months. It's because of the funding, the pressure to get that thing up so it stops burning money on the ground, I think the pressure for it to not go up much later than 2017 is intense. So, and although there are some detector issues, I've been hearing that while the telescope mirrors have passed muster and have had their thermal back testing on the ground and the instruments have been tested, there are still some detector issues with a couple of the instruments. So they're not completely ready to fully integrate the payloads and get the thing ready for launch. So it could indeed slip 6 or 8 months, but I don't expect more than that.
Right, the next question is from Esteban. How does tidal locking work?
Tidal locking is a situation where, when you have two objects interacting by gravity and they're large compared to the distance, relatively large compared to the distance between them. So the tidal force on gravity just relates to the fact that gravity is an inverse square law, depending on the inverse square of the distance. And so to take the Earth-Moon as the most proximate example where this actually happens, the force of gravity on the near side of the moon is slightly larger than the force of gravity on the far side of the moon, because the far side of the moon is further away than the near side of the moon. So there are a couple of phenomena that result from that. As you can see, it's a sort of a stretching force. So the tidal force is a stretching force, and that leads to tides. That leads to land tides. For instance, the moon doing this on the Earth leads to the tides that we see, of course, the tides in the water slops around, and twice a day we have tides. Also leads to land tides, where the probability of earthquakes is very slightly higher during full moon and new moon, when the Earth, Sun, Moon are aligned in a line, than at other times of phases of the moon. So we measure this effect with the Earth-Moon system. So the same stretching force is part of what causes the moon in this situation to stop rotating as it goes around the Earth, and eventually settle into a situation where one side faces the planet all the time. So that's tidal locking. It leads to synchronous rotation, where from the planet you only see one side of the satellite at any time. The next situation where this arises in the solar system is, of course, the nearest planet to the sun, Mercury. Mercury is tidally locked to the sun, but it's the only planet tidally locked to the sun. We have some of the moons of Jupiter and Saturn that are tidally locked to Jupiter and Saturn because there are small moons relatively close to those giant planets. So there's more than a handful of situations of tidal locking in the solar system, and we expect it to be a universal phenomenon of gravity.
The next question is from Ezekiel. To my understanding, the New Horizons probe, which is due to arrive to Pluto later this year, is going to fly by it instead of entering in orbit around it. Why not orbiting Pluto and staying longer?
Yeah, very good question. You've got something that's traveled that far for that long. Why not stick around and observe it? It's an uncomfortable fact of gravitational physics and just physics, energetic physics in general, that was just too hard to do. In orbital dynamics within the solar system, one of the hardest but most important things to do is to put a spacecraft into an orbital trajectory around a planet or a moon. And then we've, of course, done this with the inner planets. We've done this with Jupiter and Saturn. We've done it with moons of Jupiter and Saturn. But the trouble is you can't have everything. If you want to get a spacecraft to the outer solar system on a reasonable timescale, like a decade, it's going to be traveling extremely fast. And the problem out there, where there are no other objects to help you with this, is that there's no way to gravitationally brake the spacecraft. And so you can't slow it down enough to go into an orbit. And remember, of course, that Pluto is a small, low-mass object, so you'd have to somehow shave off a huge amount of velocity or kinetic energy from the spacecraft to somehow inject it into an orbit of Pluto. So when you look at the math of this, there's just no way to do it. In the inner solar system, and even in the giant planets, you have a lot more tools to help you. You can use flybys of the giant planet to just shave off kinetic energy and then inject your spacecraft into an orbit of Europa, say, or Io. But in the outer solar system, moving so fast to get there in the first place, and with no other objects to help you, you have no way to get gravity to help you put it in an orbit. So it's just going to whiz by and be gone.
Okay, Hassam asks, can we use a spiral hole to go to the past?
Spiral hole, I'm not sure what that means. Maybe if we're talking about white holes or black holes or space-time disruptions, I'll assume we're talking about that. To violate time, interesting hypothesis. It's not clear. I mean, we're in the realm of speculation. Anything to do with segmented space-time or places in space-time that are separated from our space-time are matters of speculation. Kip Thorne's written a good popular book about this. And he speculates, but he's believable because he's one of the world's most premier gravitational physicists at Caltech. So his book, which I can't remember the title of, I recommend strongly on this matter and others. Could we violate time? Well, the event horizon black hole, as I alluded to in an early question, is a place where, in principle, time freezes. Also, if you follow the theory of black holes as well as we understand it, that is the theory of black holes based on general relativity with the various embellishments and improvements of Stephen Hawking and others in the 1970s and 80s, then it is indeed possible that inside the event horizon of a black hole, you can have what's called a time-like curve and space-like curves. You can have places where you can walk along a physical line inside the black hole and move backward or forward in time at will. So time travel, hypothetically, could be possible inside, especially inside a rotating black hole, and maybe not. And Matthew's helping me by saying that the Black Holes and Time Warps is Kip Thorne's book, and it's a great book, so I recommend that. And it talks about this as well. So it's a good question, and it's a matter of speculation. Time travel, you know, it's one of the great concepts of physics and science fiction, and could nature really do that? We don't think in the conventional, normal, low-gravity universe it's possible. But in these high, intense gravity situations where space-time is convoluted and maybe sequestered off from our space-time, yes, it's possible.
Okay, John asks, relative to other planetary systems, how rare is it for a planet to have a satellite as proportionally large as the moon is to the Earth?
It's a good question, and it's an interesting issue for astrobiology because there's been an argument made called the rare Earth hypothesis that says that life is rare in the cosmos because we only know of the Earth that has life, and Earth has this particularly large moon relative to the planet size, which operates to stabilize our orbit and our seasonal cycle. Now, recently the research has muddied this by showing that the moon doesn't actually do such a great job at stabilizing our climate long term. But in general, to answer the question, this is very unusual. The moon is a particularly large satellite compared to the planet. Just look at the largest moons of Jupiter and Saturn compared to their size, or the puny moons that Mars has compared to its size. And we, of course, now attribute the large size of the moon compared to the Earth to an impact, to its formation from an impact of the infant Earth with a Mars-type projectile very early in the history of the solar system. So I think the supposition is that that situations are going to be rare because naturally you're just not going to form satellites as large as the moon relative to the Earth. but that may happen because of impacts, and it may also happen occasionally because of capture. And in a capture situation, I suppose you could have moons that were a substantial fraction of the size of the planet.
Okay, we just have 1 minute remaining, but Jose would like to know, what is the most exciting physics or astronomical phenomena you have been able to study or research?
So in my research, I work on distant galaxies and their supermassive black holes, trying to ask the question of which came first and how did they grow, because we believe every galaxy has a supermassive black hole. And I think the most exciting thing that I've observed in the last 5 years or so in surveys for distant galaxies and their black holes is our black holes at distances of probably 5 to 8 billion light years that are phenomenally large, massive, and also energetic. And these are quasars, so there are active galactic nuclei called quasars, which we talk about later in the course. The inference of the mass of the black hole we do with spectroscopy from big optical telescopes. In my case, we use the Magellan telescope in Chile. And I think the highest mass measured in surveys I've been involved in is about 3 billion times the mass of the sun. So for me, that's extraordinary. We have dead stars that are a few times the mass of the sun. They're black holes, best evidence for stellar mass black holes. We have a 4 million solar mass black hole in the center of our own galaxy. And yet in nature, out in the distant universe, there are black holes 1,000 times bigger than the black hole at the center of the Milky Way. So just the whole notion of a black hole that's billions of times the mass of the sun, to me, even though I studied it for a while, it's still pretty amazing, pretty extraordinary. And I think that's all we have time for today. So thank you very much for your participation. Great questions today, covered the full range, comments to cosmology, and we'll be back next week.